We know that order of a reaction is defined as the sum of the powers of the concentration of the reactants in the rate law expression. Let us now see what is meant by molecularity of a reaction. Molecularity is defined as the number of reacting species taking part in an elementary reaction which must collide simultaneously in order to bring about a chemical reaction. It is a theoretical quantity. We know that order is an experimental quantity, but molecularity is a theoretical quantity. It cannot be zero or a non-integer, and molecularity is applicable only for elementary reactions. Molecularity of the slowest step is found to be same as the order of the overall reaction. Now consider the decomposition of ammonium nitrate to nitrogen and water. What is molecularity equal to? It is equal to 1. Therefore, it is a unimolecular reaction. Now consider the dissociation of hydrogen iodide to hydrogen and iodine. What is molecularity equal to? It is equal to 2. Therefore, it is a bimolecular reaction. Consider the decomposition of hydrogen peroxide. Hydrogen peroxide decomposes in the presence of I- in an alkaline medium to give water and oxygen. The rate law expression for this reaction is given as rate is equal to rate constant K into hydrogen peroxide concentration into I- concentration. The reaction takes place in two steps. In the first step, hydrogen peroxide reacts with I- to give water and IO-. IO- is the intermediate formed. In the second step, hydrogen peroxide reacts with the intermediate IO- to give water, I- and O2. So the reaction here takes place in two steps, and both the steps can be considered as bimolecular elementary reactions. IO- is the intermediate formed. Out of the two steps, the first step is slow and hence it is the rate determining step. So this is the reason why the rate law expression is given as rate is equal to rate constant K into concentration of hydrogen peroxide into concentration of I-. Integrated rate equation. Let us now try to derive an expression for the rate constant K for a zero order reaction. Consider the reaction R giving P. So rate can be written as equal to minus dr by dt is equal to K into R raised to 0. K is the rate constant. But here R raised to 0 is equal to 1. And if we take dt to the other side of the equation, we get minus dr is equal to K dt. Or dr is equal to minus K dt. We have to integrate this equation. On integrating this equation, we will be able to get the relationship between the concentration of the reactant at different times and the rate constant K. So when we integrate the equation, that is integral dr is equal to minus K integral dt, we get R is equal to minus Kt plus I. Here I is the constant of integration. The next step is to find the integration constant I. For that, let the time t be taken as equal to 0, so that R will be equal to R0, the initial concentration. So equation 1 now becomes R0 is equal to minus K into 0 plus I, or from that we get the integration constant I as equal to R0. Substitute this value of I in equation 1. So the equation 1 now becomes R is equal to minus Kt plus R0. Now rearrange this equation. On rearranging this equation, we get the rate constant K as equal to R0 minus R by T, where R0 is the initial concentration of the reactant and R is the concentration of the reactant at time T. So we have the rate constant K for a zero order reaction. And how is it given as? It is given as K is equal to R0 minus R by T. Let us now see the nature of the graph obtained for a zero order reaction. For that, consider the expression R is equal to minus Kt plus R0. This equation is of the form y is equal to mx plus c. So, if a graph is plotted taking time along the x-axis and the concentration R along the y-axis, a straight line graph will be obtained. And what will be slope equal to? Slope will be equal to minus k and the intercept will be equal to r0. Let us now try to derive an expression for the rate constant k for a first order reaction. Consider the first order reaction R giving P. The rate is given as equal to minus dr by dt, which is equal to k into r raised to 1. Or we get dr by r is equal to minus k dt. We have to integrate this equation. So integral of dr by r is equal to minus k integral dt. But integral of 1 by r dr is ln r. So when we integrate, we get ln r is equal to minus kt plus I. We have to find the integration constant I. So for that, let time be taken as equal to 0, so that r will be equal to r0. So the first equation becomes ln r0 is equal to minus k into 0 plus I. Or the integration constant I will be now equal to ln r0. Substitute this value of the integration constant in the first equation. So now the equation 1 becomes ln r is equal to minus kt plus ln r0. We have to convert the ln terms to log terms. For that, multiply the ln terms by 2.303. So the equation now becomes 2.303 log r is equal to minus kt plus 2.303 log r0. Now divide throughout by 2.303. On dividing by 2.303, we get log r is equal to minus kt by 2.303 plus log r0, or kt by 2.303 is equal to log r0 by r. So what will be the rate constant k equal to? K will be equal to 2.303 by t log r0 by r. Here r0 is the initial concentration of the reactant, r is the concentration of the reactant at time t. So the rate constant k is given as k is equal to 2.303 by t log r0 by r.